Welcome to Unit 12, all about acids and bases. So what are some properties of acids and bases? I know you've heard about them before, so a lot of this is going to be a refresher, but some of it's a little new. So acids have a pH of 0 to 7. They taste sour. All of those sour candies that you love, it's because of a substance called citric acid. It's going to turn litmus paper red. Neutralizes a base to form water and a salt. Is what we call a proton donor, which we'll get more into later. And it has a high concentration of hydrogen ions / hydronium ions, which we'll also talk about a little bit later. And they are electrolytes, meaning they conduct electricity when placed in water. They also react with metals to produce hydrogen gas. On the other hand, we have bases, which have a pH of 7 to 14, so the higher end of our pH scale. The pH scale maxes out at 14. They are going to taste bitter. They turn litmus paper blue or yellow, depending on the type of litmus paper. And they neutralize an acid to form water and salt. They are proton acceptors. They have a high concentration of hydroxide ions. They are also electrolytes, and they feel slippery to the touch. Soap is a base, which is why it feels slippery on your hands. So some examples of acids and bases. Acids can be monoprotic, meaning they only have one hydrogen, such as HNO3, nitric acid, HCl, hydrochloric acid, or HC2H3O2, acetic acid. They can also be diprotic, meaning having two hydrogen ions, di meaning two, such as sulfuric acid. And they can also be triprotic, meaning having three hydrogens, such as phosphoric acid. Bases fall under similar categories, where bases can be monobasic, meaning they have one hydroxide group, such as lithium hydroxide or sodium hydroxide or potassium hydroxide. They just have that one hydroxide. Ammonium hydroxide is another great example. Bases can also be dibasic, having two hydroxide groups, such as magnesium hydroxide, calcium hydroxide. Now, when it comes to acids and bases, we can call them strong or weak. So strong means that they completely ionize, break down into ions in water. While weak means they do not completely ionize in water, meaning they do not completely break down, and some of them are going to stay bonded together instead of breaking apart. A strong acid or base does not become a weak acid or base just because we dilute it. That's not the difference. If you have a strong acid, you could add as much water to it as you want. It's still going to be a strong acid. So in other words, concentrated hydrochloric acid and dilute hydrochloric acid are both strong acids because they completely ionize in water. It has nothing to do with how much is in there. Strong acids and bases of the same molarity will react at different rates with the same metal. Strong acids and bases conduct electricity easily, whereas weak acids and bases conduct electricity poorly. So the strength of the electrolyte is also determined on whether it's a strong or weak base. Now, why do we care? So here's a kind of visual representation of what I'm talking about, where in your strong acid, everything is breaking apart into the ions, the hydrogen ions, and whatever the other part of the acid is. It is completely separated. Meanwhile, in a weak base, a weak acid, we all start together, but some of it stays together. See how it doesn't break apart and only part of it ionizes, making it different. So strong versus weak acids. So strong acids are going to 100% ionize, meaning break down into ions. All of the acid separates into ions in water, usually between a pH of 0 and 2. And some examples for you are HCl, HI, HBr, HNO3, HClO3, HClO4, and H2SO4. You are responsible for memorizing all 7 strong acids. Weak acids only partially ionize, So that means some of the molecules become ions in water and some of the acid molecules stay as molecules. They don't break down. These are going to be usually pHs between 2 and 6.5. Some examples, although technically if you were not a strong acid, if you were not one of those 7 strong acids, you were technically a weak acid. So I'm not going to ask you to memorize all the weak acids because there are way too many. But some common ones are acetic acid, hydrofluoric acid, and nitrous acid. We can also have strong versus weak bases, where once again a strong base is going to 100% ionize, meaning that all of the base separates into ions in water. These typically have a pH between 12 and 14, so the very highest end of the pH scale. Some examples are lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, cesium hydroxide, calcium hydroxide, barium hydroxide, and hydroxide. Just like the acids, you are responsible for memorizing all 8 of our strong bases. Just like in acids, weak bases are only going to partially ionize, meaning that some of the base molecules are going to stay as molecules, while some of the molecules will become ions. These typically have a pH of between 7.5 and 12. Once again, if you're not a strong base, you're technically a weak base, so I'm not going to ask you to memorize all of the examples, but some examples are ammonia and ammonium hydroxide. So there are 2 main acid-base theories. The original was Arrhenius's acid-base theory, and he stated that acids produce hydrogen ions in water, whereas bases produce hydroxide ions in water. Salts produce neither hydrogen ions nor hydroxide ions in water. So he categorized everything as an acid, a base, or a salt. And his theory was really good for describing strong acids and strong bases. But then Bronsted-Lowry came along and was like, although that's good, that's not quite right. And Bronsted-Lowry said that essentially a hydrogen ion, H+, is just a proton, because hydrogen only contains 1 proton and 1 electron. So hydrogen plus has lost that 1 electron, so it is just a proton. No neutron, no electron, just a proton. So therefore, they said that acid is a proton donor, meaning it gives up hydrogen ions, whereas bases are proton acceptors, meaning they are going to take those hydrogen ions that have been released. And this is a much more accurate description of what happens. So when an acid or base reacts with water, water can act as an acid or a base because water has a pH of 7 and therefore we consider it neutral. And this explains a lot more of what happens in our world. So based on Bronsted-Lowry's definition of acids and bases, conjugate acid and base pairs came along. And a conjugate acid and base pair is a pair of species that are related to each other by 1 hydrogen ion. So an acid is going to make what we call a conjugate base, which I often abbreviate as CB, and a base is going to make a conjugate acid, which I abbreviate as CA. The acid and base are on the reactant side of the equation. The conjugates are going to be on the product side of the equation. So let's take a look. Bronsted-Lowry said when an acid reacts with water, it produces hydronium ions, H3O+, which is going to be considered to be the conjugate acid. And the conjugate base is going to be everything left over once the hydrogen ion is removed. So we have hydrochloric acid, HCl, plus water. Remember, water can be an acid or a base. It just depends on what it's reacting with. So in our case, we know hydrochloric acid is an acid. It's in its name. So that means water has to be the base. Now remember, our conjugate base is going to be whatever loses the hydrogen. So in this case, we can see that chlorine used to be HCl, but now it's Cl-. It lost the hydrogen, so it is the conjugate base. And our hydronium ion is going to be our conjugate acid. Once again, the acid makes a conjugate base, and the base makes the conjugate acid. The conjugate acid and the conjugate base can reform to make the parent acid and base. Therefore, these reactions are called reversible. So we'll often, instead of just using a single arrow like you see above, use a two-headed arrow or double arrows in order to show it could go backward and forward. So we have HA plus H2O producing H3O plus and HA. HA is going to be our acid, H2O is going to be our base, H3O plus is our conjugate acid, and A minus is our conjugate base. This is just a general kind of formula to keep in mind. And once again, these are those double arrows I was talking about to show that the reaction could go backwards and forwards. So once again, that general formula again, the conjugate base of a strong acid is a weaker base than water. The conjugate base of a weak acid is a stronger base than water. The conjugate acid of a weak base is a stronger acid than water, and the conjugate acid of a strong base is a weaker acid than water. So once again, going back to the strong versus weak, the conjugate acids and bases vary depending on what they started out as. So let's keep going with conjugate acid-base pairs. So here's another example where you have H2SO4 plus H2O producing HSO4 plus H3O plus. So we know that H2SO4 is an acid. We know that because 1, we know it's sulfuric acid, but 2, we can tell on the other side it gives up a proton. We have H2SO4 here with hydrogen being essentially just a proton, and over here we only have HSO4 minus, meaning it lost that hydrogen, it lost that proton. That makes HSO4 minus the conjugate base because it can accept another proton. It has that minus charge, it's looking to take a proton back. H2O is therefore our base because we always have acids and base reacting, and that means H3O plus is going to be our conjugate acid because it could donate another proton if it wanted to. All right, let's do some more practice. I'm going to give you an acid, and you are going to tell me what the conjugate base is. So these are your acids, and I want you to pause this video and come back once you've figured out the conjugate base for all of them. Please actually try this. I know many of you just wait till the answers show up, but then the next day in class you're confused about how to do this because you didn't practice on your own. So pause the video, come back when you're done. All right. So up first, we have HNO3, which is going to lose a hydrogen to just become NO3 minus. H2O loses a hydrogen to become OH minus. H3O plus loses a hydrogen to become H2O. H2SO4 loses a hydrogen to become HSO4 minus. And HCO3 minus loses a hydrogen to become HCO3 2 minus. All the difference is between one side and the other is we've taken away one hydrogen. You can do the same thing where given a base, you can come up with the conjugate acid. So once again, I want you to pause this video and come back when you are done. All right, so when we're going from a base to a conjugate acid, they are receiving a hydrogen. So OH minus gains a hydrogen to become H2O. H2O gains a hydrogen to become H3O plus. HCO3 minus is going to gain a hydrogen to become H2CO3. SO4 2 minus is going to gain one hydrogen to become HSO4 minus. And ClO4 minus is going to gain a hydrogen to become HClO4. This time, all I did was go from one side and add a hydrogen to go from a base to the conjugate acid. For conjugate acids and bases, you are going to be asked to determine which is an acid, base, the conjugate acid, and the conjugate base for reaction. So let's practice that. You were given these two reactions, and you were asked to determine what is the conjugate acid, what is the conjugate base, and what is the acid, and what is the base. So I want you to pause this video and come back when you are done. All right, so up first, you should have been able to figure out that HBr is going to be our acid. It's hydrobromic acid. But we can also tell from one side to the other, it loses its hydrogen. And remember, acids always lose their hydrogen. So that's our acid, which makes water our base because water is going to behave however the opposite of the other one. Now, once again, whatever lost the hydrogen becomes the conjugate base. So Br minus is going to become our conjugate base. And whatever gained the hydrogen becomes our conjugate acid. So that is H3O plus. Now this one was a little trickier. You had NH3 plus H2O. So you really had to use your what gained protons and what lost protons. So when we took a look, we noticed that we have NH3 and we have NH4 plus. So NH3 gains a hydrogen. Since it gained a hydrogen instead of losing a hydrogen like happened up above, we know that means it's going to be a base. And since water is always going to behave as the opposite, that means it's an acid. So when we have a base, and it accepts a proton, it becomes the conjugate acid. And when you have an acid and it loses a hydrogen ion, like happened to the OH minus, it becomes the conjugate base. So you notice that water is behaving as either an acid or a base in these equations. You can't reliably predict it until you predict the other one. And that's because water is the most common amphoteric substance, and that means it is a substance that can act as both an acid and a base. The reason for that is because of how water ionizes. If you have two water molecules, H2O plus H2O, it ionizes to be H3O plus and OH minus, literally the acid and the base ions essentially. It is creating a conjugate acid and a conjugate base when it ionizes, thus meaning it is an acid and a base. That's because water is both accepting and donating protons. Water will act as a base when it's reacted with an acid, and it will act as an acid when it's reacted with a base. Water does have a pH of 7, which means we consider it neutral. So it produces that hydronium ion, the H3O plus. Oftentimes you're going to see me just abbreviate it as H plus to save time, but either is technically correct. And the hydronium ion concentration is what determines the pH of the substance. So the concentration of hydronium is why water has a pH of 7 and why acids and bases have the pHs we do. We're going to be diving more into that in our next video.